Hello everyone. Today I'm going to explain about my Physics Term 1 project called Reenacting the Past. First, we have the big question for this semester, which is why do visionary leaders adapt? Followed by the focus question for this physics term, which is how can humans analyze transformations based on physics concepts and laws in day-to-day life activities? So we have the outcomes as well taught in this physics term. The first one being able to develop a forward-thinking design based on the understanding of Newton's law of motion, as well as able to analyze a daily life problem based on the principle of work, energy, and power. So let's dive right into the first concept, which is Newton's law of motion. In this slide, we can see an illustration of three people standing, which is a great example of Newton's first law of motion, stating that every object will remain at rest unless compelled to change its state by the action of an external force. The free body diagram shows the gravitational force, which always goes down regardless of the position of the object, and a normal force, which is the force that a surface exerts on an object, as you can see here. So in this picture, if they were to just stay still, according to Newton's first law, they will remain in the same spot unless an external force is applied, such as the motion of moving, being pushed, or being pulled. Moving on, in this picture, we are able to see an NBA player, Steph Curry, about to make a pass, which is an excellent example of Newton's second law, stating that the force, or F, is the product of an object's mass and its acceleration, such that F equals m multiplied by a, F being the force, m being the mass, and a being the acceleration. In this free body diagram, we see that there are various forces, which are gravitational force, who always goes downwards, applied force, which is the force applied to an object, in this case the basketball at Curry's hand, as well as a friction force, which goes oppositely with the ball's motion. So, back to the picture, if we were to calculate the acceleration of the basketball that Curry threw, we would need to know how much force was applied to the ball, as well as the ball's mass. Moving on, we have a picture of three people leaning into a park bench. This is an example of Newton's third law, which states that for every action, there is an equal and opposite reaction. From the free body diagram, we are able to analyze the forces which are happening in the picture. First, we have the gravitational force, which is always downwards. Then we have applied force, which is the guy leaning on the right, leaning towards the bench. Then we have the friction force, which is the resistance to motion of one of the objects moving relative to the other, opposite to the applied force. And lastly, we have tension, which is between the waist bag hanging around the guy's neck, with the rub of the bag creating tension between the two objects. So as you can see here, it creates tension. In this picture, we are able to see the guy on the right leaning towards the bench as stated previously, which exerts leaning force as an action, as well as, and the reaction being the bench pushing the guy's body back. So, from this and the previous pictures, we are able to take note of the usage of Newton's three laws in our daily life activities. Moving on, we have the second concept taught in this term, which is kinetic, potential, and mechanical energy. So here we see an illustration of a guy cycling up a hill or a mountain. And here we have a nice little illustration of the guy's movement over time. So, the mass of the guy is 65 kilograms, and the mass of the bike is 13 kilograms. Next, so we put that into our calculations. Our total mass, that gives us the guy's mass and the bike's mass as well. So we get 78 kilograms in total. And the height is on point A, you have 0 meters because it's the starting point. On point B, you have 2 meters, C 4 meters, and D 6 meters. So here we have a table that I've made to make it easier to visualize and calculate. What I like to do with these types of calculations is to find the potential energy for the object's greatest height first. So in this case, 6 meters. This will give me the exact value of the mechanical energy, because the kinetic energy will always be at zero at the object's peak height, and the potential energy will always be at its maximum. So from there, I can derive mechanical energy by subtracting the potential energy from the kinetic energy, which in this case is zero. So the total energy is the same with the potential energy. Once I found the mechanical energy, or the total energy, then by the law of energy conservation, which is this one right here, it states that the energy cannot be destroyed or created. So we know that the mechanical energy will always remain the same regardless of the potential energy or the kinetic energy. And from there, all I had to do was substitute everything into the equation to solve for kinetic energy and its speed as well. For its speed, I modified the formula for kinetic energy, 1/2 mass times velocity squared, in order to solve for speed. I had to isolate the velocity, which means that I had to divide kinetic energy by 1/2 times its mass. And from there, it's just a matter of substituting and doing math regularly. So in conclusion, Newton's laws of motion are important because they are the foundation of classical mechanics, one of the main branches of physics. Furthermore, both Newton's law and the law of energy conservation are able to analyze transformations happening all around us. So the answer for the focus question is, after doing the project, I can see that both Newton's laws of motion and the law of conservation energy are able to help us analyze transformations happening all around us on a day-to-day basis, as stated previously. Finally, we have the big question answer, which is, as leaders of tomorrow, being able to adapt is one of the must-have assets in our disposal. Without it, we won't be able to keep up with the constant changes of the world. That's all for me. Thank you for listening.